Welcome to week 13 of the mathematics track, Solving Rational Equations. This lesson belongs to module Math-1, Phase A, and is designed for approximately 120 minutes of study, followed by 10 practice problems. The central objective of this session is twofold. First, students will acquire a systematic procedure for solving equations that contain rational expressions, equations in which at least one term involves a polynomial quotient. Second, students will develop the analytical discipline of verifying candidate solutions against the domain of the original equation. The overarching principle is straightforward but frequently neglected. Multiplying both sides of an equation by a variable expression is not, in general, a reversible operation. When that expression evaluates to 0 for a particular value of the variable, the multiplication step can introduce solutions that satisfy the transformed equation but violate the domain of the original. These are termed extraneous solutions, and their detection requires explicit verification, a habit that transfers directly to numerical stability practices in machine learning. By the end of this lesson, students should be able to identify domain restrictions, compute the least common denominator, clear denominators systematically, solve the resulting polynomial equation, and, critically, verify every candidate against the original domain before reporting a solution. This lesson is sponsored by Subthesis, a self-study platform offering structured resources in mathematics, computer science, and machine learning. Subthesis provides curated learning paths that integrate foundational mathematical reasoning with applied computational thinking, precisely the kind of cross-disciplinary bridge that this lesson exemplifies when it connects rational equation domain analysis to numerical stability in machine learning systems. More information is available at subthesis.com. A rational equation is defined as an equation containing at least one rational expression, that is, a quotient of polynomials, on one or both sides. The solution strategy that governs every problem in this lesson consists of two stages. First, clear all denominators by multiplying through by the least common denominator. Second, verify each candidate solution against the original equation's domain. The verification step is essential because multiplying by a variable expression can introduce candidates that satisfy the cleared equation but render the original expression undefined. This is not a rare edge case. It is a structural feature of the method. The agenda for this session proceeds as follows. We begin with the 5-step procedure for solving rational equations, then work through a detailed example. We examine the cross-multiplication shortcut and its limitations, analyze the extraneous solutions phenomenon with a counterexample, and connect the domain verification habit to numerical stability in machine learning. We then conduct a 10-question practice quiz and conclude with a recap and preview of next week's material on radicals and rational exponents. A rational equation is defined as an equation containing at least one rational expression, that is, a quotient of polynomials, on one or both sides. The solution strategy that governs every problem in this lesson consists of two stages. First, clear all denominators by multiplying through by the least common denominator. Second, verify each candidate solution against the original equation's domain. The verification step is essential because multiplying by a variable expression can introduce candidates that satisfy the cleared equation but render the original expression undefined. This is not a rare edge case. It is a structural feature of the method. The agenda for this session proceeds as follows. We begin with the 5-step procedure for solving rational equations, then work through a detailed example. We examine the cross-multiplication shortcut and its limitations, analyze the extraneous solutions phenomenon with a counterexample, and connect the domain verification habit to numerical stability in machine learning. We then conduct a 10-question practice quiz and conclude with a recap and preview of next week's material on radicals and rational exponents. The procedure for solving rational equations is a 5-step algorithm, and each step is non-optional. Step 1. Identify domain restrictions. Before any algebraic manipulation, determine every value of the variable that would make any denominator in the original equation equal to 0. Record these excluded values explicitly. Once denominators are cleared, the information needed to identify extraneous solutions is no longer visible in the equation. Step 2. Find the least common denominator. Compute the least common denominator of all rational expressions present in the equation. The least common denominator must include every distinct factor, both constant and variable, that appears in any denominator. Step 3. Multiply both sides by the least common denominator. This step eliminates all fractions simultaneously, reducing the rational equation to a polynomial equation. If the least common denominator has been computed correctly, every denominator cancels completely. Step 4. Solve the resulting polynomial equation. In the context of this course, the polynomial will typically be linear or quadratic, both of which students have practiced extensively in prior weeks. Step 5. Verify each candidate against the domain. Any candidate that coincides with an excluded value from step 1 is extraneous and must be discarded. This step is mandatory. Multiplying by a variable expression is not a reversible operation when that expression equals 0, and the verification step is where this irreversibility is accounted for. Note the deliberate emphasis on the boundary between steps 4 and 5. Arriving at a correct algebraic solution to the cleared equation does not guarantee a valid solution to the original equation. A common pedagogical error is to treat step 5 as optional once the polynomial solves cleanly. In fact, the cleaner the algebra, the more tempting it is to skip verification, and the more likely one is to miss an extraneous root. We now apply the 5-step procedure to a concrete problem. Solve 1 or x plus 1 or 2 equals 3 or 4. Step 1. Domain restrictions. The variable x appears in the denominator of the first term, so x cannot equal 0. The denominators 2 and 4 are constants and impose no additional restrictions. Thus the domain is all real numbers except 0. Step 2. Least common denominator. The denominators are x, 2, and 4. To compute the least common denominator, we take the least common multiple of the constant factors. Least common multiple of 2 and 4 is 4, and multiply by the variable factor x, yielding least common denominator equals 4x. Note that the least common denominator is not simply the product of all denominators. We use the least common multiple to avoid unnecessary complexity in the resulting equation. Step 3. Multiply both sides by 4x. On the left side, 4x multiplied by 1, or x, gives 4, and 4x multiplied by 1, or 2, gives 2x. So the left side becomes 4 plus 2x. On the right side, 4x multiplied by 3, or 4, gives 3x. The equation is now 4 plus 2x equals 3x. Step 4. Solve. Subtracting 2x from both sides yields 4 equals x, hence x equals 4. Step 5. Verify. The candidate x equals 4 does not coincide with any domain restriction. It is not 0, so it remains in the domain. Substituting back into the original equation, 1 or 4 plus 1 or 2 equals 1 or 4 plus 2 or 4 equals 3 or 4, which equals the right-hand side. The solution x equals 4 is confirmed as valid. Two pedagogical observations merit attention here. First, cross-multiplication was not employed because the equation involves 3 rational terms rather than 2. Cross-multiplication is a special case of the least common denominator method, applicable only when exactly 2 fractions are set equal. Second, step 5 was non-trivial even in this straightforward problem. One must explicitly confirm that the candidate does not violate the domain, rather than assuming validity from the algebraic consistency of the solution. Cross-multiplication is a widely recognized shortcut for solving equations of the form a or b equals c or d. The equivalence states that AD equals BC, provided B and D are both non-zero. It is important to understand that cross-multiplication is not an independent technique. It is simply the least common denominator method applied to a two-fraction equation whose least common denominator is the product BD. To see why this is the case, consider multiplying both sides of A or B equals C or D by BD. On the left side, the B in the denominator cancels with the B in BD, leaving AD. On the right side, the D in the denominator cancels with the D in BD, leaving BC. The result, AD equals BC, is precisely the cross-multiplied form. The critical limitation of cross-multiplication is its scope. It applies exclusively when the equation consists of exactly 2 rational expressions set equal to each other. If the equation contains 3 or more fractions, such as 1 or x plus 1, or 2 equals 3 or 4, cross-multiplication cannot be applied directly. Attempting to do so is a common source of error among students who have internalized the shortcut without understanding its derivation. In such cases, one must revert to the full least common denominator procedure described on the previous slide. Furthermore, the domain restrictions b not equal to 0 and d not equal to 0 must still be recorded and verified after solving. The act of cross-multiplying removes the denominators from the written equation, but it does not remove them from the problem's domain. Any candidate that violates these restrictions remains extraneous and must be discarded. This point is frequently overlooked when students treat cross-multiplication as a mechanical rule rather than a consequence of the least common denominator method. This is example 2, a harder equation. We want to solve the quantity x plus 2 divided by the quantity x minus 3 plus 1 equals 5 divided by the quantity x minus 3. In step 1, we identify the domain restriction. Since x minus 3 appears in the denominator, x cannot equal 3. In step 2, the least common denominator is the quantity x minus 3. Multiplying every term on both sides by the least common denominator, we get x plus 2 plus x minus 3 equals 5. Simplifying, 2x minus 1 equals 5, so x equals 3. But here is the critical moment. Step 3 is the domain check. We found x equals 3, but x equals 3 makes the denominator x minus 3 equal to 0. That means x equals 3 is extraneous. It must be rejected. The equation has no solution. The key insight here is that valid algebra can lead to a number that the domain forbids. Always verify your candidate before declaring it a solution. This slide addresses the extraneous solutions phenomenon, which constitutes the single most important conceptual challenge in this lesson. Consider the equation 2 or x1 equals x plus 1 or x1. Both sides share the denominator x1, so the domain restriction is x not equal to 1. Multiplying both sides by x1 clears the denominators, yielding 2 equals x plus 1, and hence x equals 1. However, substituting x equals 1 back into the original equation produces 0 in both denominators. The original expression is undefined at x equals 1. The candidate is therefore extraneous, and the equation has no solution. The underlying issue is structural, not arithmetic. Multiplying both sides of an equation by a variable expression is a valid algebraic operation only when that expression is non-zero. When the multiplier passes through 0, that is, when it evaluates to 0 for some value of the variable, the multiplication becomes irreversible. Specifically, it collapses distinct values on one or both sides of the equation, potentially creating the appearance of equality where none existed in the original. This is why the verification step in the 5-step procedure is not merely a good practice, but a logical necessity. The cleared equation and the original equation are not logically equivalent. The cleared equation is a consequence of the original, given non-zero denominators, but not vice versa. Any solution to the original is necessarily a solution to the cleared equation, but the converse does not hold. Verification is the step that enforces this asymmetry. Students should note that extraneous solutions are not a sign of an error in the algebra. The algebra may be entirely correct. The issue is that the operation of multiplying by a variable expression enlarges the solution set. The verification step is the mechanism for restoring the original solution set. This slide covers the 4 most common mistakes students make when solving rational equations. Mistake number 1 is forgetting the domain check. Always identify which values of x make any denominator 0 before you start solving. If your final answer is one of those excluded values, it is extraneous and must be rejected. Mistake number 2 is multiplying only one side by the least common denominator. Remember that whatever you do to one side, you must do to the other. Every single term on both sides needs to be multiplied. Mistake number 3 is choosing the wrong least common denominator. The least common denominator must include each distinct factor raised to its highest power across all denominators. Using a larger common multiple will work, but it creates bigger numbers and more room for arithmetic errors. Mistake number 4 is applying cross-multiplication when there are more than 2 fractions. Cross-multiplication only works for equations in the form a over b equals c over d, meaning exactly one fraction on each side with nothing else added. If there are additional terms, you must use the least common denominator method instead. The pro tip at the bottom reinforces the habit of always substituting your answer back into the original equation to confirm it does not produce a 0 denominator. This slide establishes the bridge between the algebraic discipline of domain verification and the computational discipline of numerical stability in machine learning. Many fundamental machine learning formulas involve division. The softmax function requires dividing by a sum of exponentials. Bayesian inference involves dividing by marginal probabilities. Normalization procedures divide by standard deviations, or norms. In each case, the denominator can, in principle, approach 0, or become numerically indistinguishable from 0 in finite precision arithmetic, producing undefined or infinite results, the computational analog of evaluating a rational expression at a domain-excluded value. 3 defensive rules follow directly from the domain-checking habit developed in this lesson. First, never divide by a quantity that could be 0 or near 0 without adding a small stabilizing constant, typically epsilon equals 10 to the negative 8, to the denominator. Second, never compute the logarithm of 0. Instead, compute log p plus epsilon to ensure the argument remains strictly positive. Third, verify every formula against edge cases, particularly x equals 0, very large x, and very small positive x, before deploying it in a training loop. The tagline for this transfer is, "Domain check now, not a number guard later." The habit of asking whether the denominator can be zero is precisely the habit that prevents not a number crashes in production machine learning systems. The mathematical content is identical, only the context changes from pencil and paper algebra to floating point computation. Students who internalize this connection will find that numerical stability is not an additional topic to learn, but a natural extension of the algebraic discipline they are building this week. We now transition to the practice quiz, which consists of 10 questions designed to assess understanding of the material covered in the preceding slides. The quiz is structured in 2 segments. The first 6 questions drill procedural competency, computing LCDs, applying cross-multiplication where appropriate, and solving rational equations through the standard 5-step method. The final 4 questions target higher-order understanding, the rationale for the verification step, the identification of extraneous solutions, and the conceptual connection between domain analysis and numerical stability in machine learning. Students are encouraged to pause after each prompt and attempt the problem independently before the answer is revealed. The pedagogical value of the quiz depends on genuine engagement with each problem. Reading through both prompt and answer in sequence without attempting the problem first converts the exercise from active retrieval practice into passive review, which is substantially less effective for long-term retention. Question 1. Solve. X over 2 equals 6 over 4. The answer choices are A. X equals 1, B. X equals 3, C. X equals 6, D. X equals 12. Allow a brief pause for independent problem solving before revealing the answer. The correct answer is B. X equals 3. This is a two-fraction equation, so cross-multiplication applies directly. 4x equals 2 times 6 equals 12. Hence, x equals 12 over 4 equals 3. Alternatively, one may simplify the right-hand side first. 6 over 4 reduces to 3 over 2, so x over 2 equals 3 over 2, giving x equals 3 immediately. The distractor x equals 6, choice C, arises from a common error pattern. The student multiplied one side by the least common denominator without doing the same to the other, effectively doubling the answer. Choice D, x equals 12, reflects a direct multiplication of the two numerators, which has no algebraic basis but is a frequent guess under time pressure. Question 2. What is the first step in solving 1 over x plus 1 over 2 equals 3 over 4? The answer choices are A. Add fractions on the left side, B. Multiply both sides by the least common denominator, which is 4x, C. Divide both sides by x, D. Square both sides. Allow a pause for reflection before revealing the answer. The correct answer is B. The first step in the standard procedure is to multiply both sides by the least common denominator to clear all denominators simultaneously. In this equation, the denominators are x, 2, and 4, so the least common denominator is 4x. Multiplying through by 4x converts the rational equation into the polynomial equation 4 plus 2x equals 3x, which is straightforward to solve. Choice A, adding fractions on the left side, is not incorrect in principle. One could combine 1 over x and 1 over 2 into a single fraction with a common denominator and then cross-multiply with 3 over 4. However, this approach introduces additional algebraic steps and increases the risk of arithmetic error. the least common denominator method is preferred precisely because it clears all denominators in a single operation. This question also reinforces the limitation of cross-multiplication noted on the earlier slide. Cross-multiplication cannot be applied here because the equation contains 3 rational terms rather than 2. Question 3. Free response. Solve. 2 over x equals 4. Express your answer as a single number. Allow a pause for independent work before revealing the answer. The correct answer is x equals 1 over 2. The solution proceeds by multiplying both sides by x, yielding 2 equals 4x, and dividing both sides by 4 to obtain x equals 2 over 4 equals 1 over 2. An equivalent approach is to take reciprocals of both sides. X over 2 equals 1 over 4. Hence, x equals 2 over 4 equals 1 over 2. Verification. Substituting x equals 1 over 2 back into the original equation gives 2 divided by 1/2 equals 4, which confirms the solution. Additionally, x equals 1 over 2 does not equal 0, so it lies within the domain of the original equation. The most common error on this problem is x equals 2, which arises from misreading the equation as stating that x equals the numerator. The distinction between x appearing in the numerator versus the denominator is fundamental, and this question serves as a diagnostic for whether the student attends to the structural position of the variable. Question 4. Free response. Solve. The quantity x plus 1 divided by 3 equals 5 over 6. Allow a pause for independent work before revealing the answer. The correct answer is x equals 3 over 2. This equation consists of 2 fractions set equal to each other, so cross-multiplication is applicable. Cross-multiplying yields 6 times the quantity x plus 1 equals 3 times 5 equals 15. Expanding the left side, 6x plus 6 equals 15. Subtracting 6 from both sides, 6x equals 9. Dividing by 6, x equals 9 over 6 equals 3 over 2. Verification confirms the result. Substituting x equals 3 over 2 gives the quantity 3 over 2 plus 1 divided by 3, which equals 5 over 2 divided by 3, equals 5 over 6, matching the right-hand side. There are no variable denominators in this problem, so no domain restrictions apply. A common procedural error on this problem involves the distribution step. Some students write 6 times the quantity x plus 1 as 6x plus 1, forgetting to distribute the 6 to the constant term. The remedy is to expand explicitly and verify that every term in the parentheses has been multiplied by the factor outside. Question 5. Why must we check candidate solutions in rational equations? The answer choices are A. To simplify the answer. B. To verify that no candidate makes a denominator 0. C. To find additional solutions. D. To convert to decimals. Allow a brief pause for reflection before revealing the answer. The correct answer is B. The verification step is necessitated by the fact that multiplying both sides of an equation by a variable expression, even the least common denominator, can introduce solutions that satisfy the cleared equation but not the original. As discussed on the extraneous solutions slide, this occurs because multiplication by a variable expression is not a reversible operation when that expression equals 0. The set of solutions to the cleared equation is a superset of the solutions to the original. Verification is the mechanism for restricting back to the original solution set. Choice A is empirically false. Many rational equations have a unique solution, and some have no solution at all. Multiplicity of solutions is neither a necessary feature of rational equations nor the reason for verification. Choice C mischaracterizes cross-multiplication, which is entirely reliable within its scope of application, two-fraction equations. Choice D commits a category error. The fact that rational numbers form an infinite set is irrelevant to the solution procedure for rational equations. This question targets conceptual understanding rather than procedural fluency. A student may be able to solve rational equations correctly by rote application of the five-step procedure without understanding why step 5 is necessary. This question identifies whether that understanding is present. Question 6. Solve. X divided by the quantity x minus 1 equals 2. The answer choices are A. X equals negative 1, B. X equals 2, C. X equals 1, D. X equals 0. Allow a brief pause for independent problem solving before revealing the answer. The correct answer is B. X equals 2. This is a two-fraction equation. The right-hand side, 2, can be written as 2 or 1, so cross-multiplication applies. Cross-multiplying. X times 1 equals 2 times x1, which gives x equals 2x2. Subtracting x from both sides, 0 equals x2, hence x equals 2. The domain restriction is x not equal to 1, since x1 appears in the denominator. The candidate x equals 2 is not equal to 1, so it satisfies the domain restriction and is a valid solution. Verification. 2 or 2, 1 equals 2 or 1 equals 2, confirming the answer. Choice A, x equals 1, arises from pattern matching the denominator rather than solving the equation. This is a particularly instructive distractor because x equals 1 is precisely the value excluded from the domain. Selecting it indicates that the student has confused the domain restriction with the solution. Choice D, no solution, would be correct only if the algebraic candidate were extraneous, but in this case the candidate x equals 2 passes the domain check. The no solution option tests whether students can distinguish between equations that have extraneous solutions, and hence no valid solution, and equations whose candidates happen to survive verification. Question 7. If we try to solve 1 divided by the quantity x minus 2 equals 1 divided by the quantity x minus 2, what does the domain check tell us? The answer choices are A. All real numbers are solutions. B. X equals 2 is the only solution. C. No solution because x equals 2 is excluded. D. We need more information. Allow a brief pause for reflection before revealing the answer. The correct answer is B. X not equal to 2. Both sides of the equation are the identical expression, so the equation is an identity. It holds for every value of x at which the expression is defined. However, the expression 1 or x comma 2 is undefined at x equals 2 because the denominator equals 0. Therefore, the solution set is all real numbers except 2, written x not equal to 2. This question is designed to surface a subtle but important distinction between an identity and all real numbers. An identity is an equation that holds for every value in its domain, but the domain may exclude certain values. The statement all real numbers, choice A, asserts that the solution set includes every real number without exception, which is false when the domain has exclusions. The gap between these two concepts is precisely the content of domain analysis. Choice C, x equals 2, represents a fundamental misunderstanding. X equals 2 is the one value that is not in the solution set. Choice D, no solution, is the opposite extreme and is also incorrect. This question thus tests the student's ability to reason about the interplay between algebraic truth, the equation is an identity, and domain constraints. The identity has a punctured domain. Question 8. Free response. Solve. 1 over x plus 2 equals 5. Allow a pause for independent work before revealing the answer. The correct answer is x equals 1 or 3. The solution employs the isolate then invert strategy. First, subtract 2 from both sides to isolate the rational term. 1 or x equals 3. Then take the reciprocal of both sides. X equals 1 or 3. Verification. 1 or 3 plus 2 equals 3 plus 2 equals 5, which matches the right-hand side. The domain restriction is x not equal to 0, and 1 or 3 is not 0, so the solution is valid. This problem drills an important pattern that recurs in applications. When a rational expression appears as one term in a sum or difference, the first step is to isolate the rational term algebraically before clearing the denominator. A common error is to attempt the reciprocal operation before isolating, that is, to try to take the reciprocal of both sides while the additive constant is still present. This does not produce the correct result because the reciprocal of a sum is not the sum of the reciprocals. 1 or a plus b is not equal to 1 or a plus 1 or b. Students who make this error are applying a linear operation rule to a nonlinear function, a misconception that merits explicit correction. The isolate then invert pattern also has direct analogs in solving for parameters in machine learning. When a formula of the form c equals f of x plus k must be solved for x, the first step is always to subtract k before applying f inverse. Question 9. If x equals 0 makes a denominator 0, then x equals 0 is what? The answer choices are a valid solution, b, extraneous, meaning it is excluded from the domain, c, a complex number, d, undefined only in certain cases. Allow a brief pause for reflection before revealing the answer. The correct answer is B, extraneous. If a candidate solution makes any denominator in the original equation equal to 0, that candidate lies outside the domain of the original equation and must be discarded, regardless of whether it satisfies the cleared, denominator-free equation. The domain of the original equation takes precedence over the algebra of the cleared equation. This is the central principle of Step 5 in the 5-step procedure. This question reinforces the recurring theme of Week 13. Domain analysis is not ancillary to the solution procedure, but constitutive of it. The cleared equation is a derived object, constructed by multiplying both sides by the least common denominator. Its solution set is broader than that of the original equation, precisely because the multiplication can introduce values that make the least common denominator 0. Verification against the domain is the corrective mechanism. Choice A reflects the error of privileging the cleared equation over the original. Choice C, always required, is semantically incoherent in this context and serves as a distractor for students who have not engaged with the domain analysis concept. Choice D, independent, similarly indicates a lack of engagement with the relationship between the candidate and the domain. Question 10. Reflection. How does this lesson on solving rational equations connect to numerical stability in machine learning? The slide shows 3 examples of machine learning scenarios where division by zero or near zero values can cause problems. Allow a moment for students to think about the common thread connecting all three before revealing the answer. The connection is direct and substantive. Many core machine learning computations involve division. The softmax function divides each exponentiated logit by the sum of all exponentiated logits. Bayesian inference divides a joint probability by a marginal probability. Batch normalization divides centered activations by the standard deviation. In each case, the denominator can approach zero, either exactly in degenerate inputs or effectively in finite precision floating point arithmetic, producing undefined or infinite results. The defense in machine learning is structurally identical to the domain check in rational equations. Before dividing, verify that the denominator cannot be zero or near zero. The standard implementation adds a small stabilizing constant, typically epsilon equals 10 to the negative 8, to the denominator. For the softmax function specifically, the numerically stable implementation subtracts the maximum input value before exponentiating, which prevents both overflow, exponentials becoming too large for floating point representation, and underflow, the denominator becoming too small. Division by zero and log zero are among the most common sources of not a number errors in machine learning training loops. The domain verification discipline practiced in this lesson, the habit of always asking whether the denominator can be zero, is the algebraic precursor to the not a number guarding discipline that production machine learning engineers rely on daily. The mathematical content is the same, only the computational context differs. This slide recapitulates the central content of Week 13, Solving Rational Equations. The core procedure consists of two stages. Clear all denominators by multiplying both sides by the least common denominator. Then, verify each candidate solution against the domain of the original equation. The verification step is not optional. It is a structural necessity arising from the fact that multiplication by a variable expression can enlarge the solution set. Three families of errors were identified and addressed throughout the lesson. The first is the extraneous solution trap, failing to verify candidates against the original domain, thereby reporting a value that satisfies the cleared equation but renders the original equation undefined. The second is the wrong least common denominator trap, computing the least common denominator incorrectly, typically by using the sum or product of denominators rather than their least common multiple. The third is the cross-multiply too much trap, applying the cross-multiplication shortcut to an equation with three or more fractions, which exceeds the scope of that method. The lesson's applied connection, domain checking as the algebraic precursor to not a number guarding in machine learning, should be understood not as a pedagogical embellishment, but as a genuine structural parallel. The mathematical discipline of asking, can the denominator be zero, before proceeding with division is identical in both contexts. Students who carry this habit forward will find that numerical stability in computational settings is a natural extension of, rather than a departure from, the algebraic reasoning practiced this week. Next week's lesson introduces radicals and rational exponents, completing the algebraic toolkit for expressions involving roots and fractional powers. The key content areas are as follows. First, students will learn the dual notation. The nth root of x is equivalent to x raised to the power 1 or n. This notational equivalence is not merely cosmetic. It enables the application of exponent rules to radical expressions, substantially simplifying algebraic manipulation. Second, students will encounter the radical equation trap, which is structurally analogous to the extraneous solutions phenomenon studied this week. Squaring both sides of an equation, the standard technique for eliminating radicals, is a many-to-one operation that can introduce extraneous solutions, just as multiplying by a variable expression did in rational equations. The verify by substitution discipline built this week transfers directly. Third, students will work with the identity. The square root of x squared equals the absolute value of x, not simply x. This distinction is frequently overlooked and leads to sign errors when working with negative values of x. Fourth, the machine learning connection extends to inverse square root scaling, which appears in optimizer learning rate schedules such as the atom optimizer and in attention mechanisms such as scaled dot product attention. The conceptual thread connecting this week and next is the discipline of accounting for the non-invertibility of algebraic operations. Multiplication by a potentially zero expression this week, and squaring, a many-to-one map, next week. Both require post-solution verification for the same structural reason. That concludes this week's lesson on solving rational equations. To summarize the session's principal contributions, students have learned a systematic, 5-step procedure for solving rational equations, with particular emphasis on domain analysis and the verification of candidate solutions. The extraneous solutions phenomenon has been examined both as a procedural hazard and as a consequence of the non-invertibility of multiplication by a variable expression. The connection between algebraic domain checking and numerical stability in machine learning has been established as a substantive structural parallel, not merely an analogy. If this lesson has been useful, please consider engaging with the platform's recommendation features, likes, subscriptions, and similar signals, as these help surface the material for other learners who may benefit from it. This lesson is sponsored by Subthesis. Additional self-study resources in mathematics, computer science, and machine learning are available at subthesis.com. We look forward to continuing next week with radicals and rational exponents.